Since we already passed a few minutes, I think you can already get started.
Yeah, okay. So, good afternoon, everybody. I'm Sheelu from Marthoma College, Shivadara. And thank you for the invitation for giving a talk in the research school, the summer school. And sorry for the delay taking into the, I have some network issues here. That's why the delay happens. Okay, I hope you all are enjoying the school and there will be some problems related to the online mode because you were not able to interact with the speakers physically and you cannot actually enjoy the IUCAA environment. So I hope maybe in the coming years you can come and visit IUCAA and will get you more you will be getting more information. Okay, so today I will be explaining in brief some of the machine learning applications in astronomy. So okay, okay. Is the slide changing in your screen, right?
Yes, it is.
Yeah, okay. By hearing the word machine learning, what you are thinking about machine learning? Okay, so it's like we all are using different machine learning applications in our day-to-day life, and in many of these cases, we don't even know we are actually using it in our life, like in our YouTube searches, Facebook post, and everything, any recommendation systems, everything. We are using all these things. So the most important thing is how can we teach the machines about about a thing. So that is the most important question. Okay, by hearing the word even machine learning, what you mostly think about is you are thinking about the intelligent machines. Okay, how can we make an intelligent machine? Can we teach intelligence? Can we teach intelligence to someone? We know that intelligence is actually our ability to adapt to a situation. But we are talking about intelligent machines. That means we are making some of the machines more intelligent, right? So how it is possible? For that, we are using AI, the artificial intelligence, and it refers to a machine that can be that means, sorry, that can refers to a machine in case they can adapt to a given situation and maximizes its chances for success. What it means exactly? That means the machine should adapt to a current situation and it should identify, or it's like it should maximize the chances of success during each of this prediction. Okay, so what is machine learning? It is simply teaching computers to mimic human human ability to learn and make decisions. Okay, so it is we are actually thinking in such a way that we are going to teach each machines to think like human or to make decisions like a human being. So if you check in internet, you will get a lot of different kind of definitions, and one of it is written here. It is a subfield of AI. Okay, but we know that the humans that we learn from experiences, right? We can distinguish things, or we are making a decision depending on our past experiences. We know some information, so we are basic knowledge is there, and we have some experiences, and then we use these to make decisions. Okay, so how can you make a machine to take decisions using these experiences. Do the machines have any experience? What machines exactly do is they just follow the instructions that are given in a file or a program, right? So how can we train the machine? So training a program with examples, experiments, or experiences. What is experience? That are the data, right? So that the machines can easily identify or recognize the patterns within the data, and it makes predictions based on this data and complete the task. So that is what is exactly happening in a machine learning. So what is the basic difference between a classical programming and a machine learning program? A classical program means you have some instructions or basic rules and the data required for the program, which will give you an output or the answer, right? So if say you want to find the root of a root of an equation, you have these equations, and you have the basic values for x and y, etc. Then you will find the root using a program. That is a simple classical programming. And in case of machine learning, it is different. But in machine learning, you have both the data and the answer with you. What you are actually trying to program or model is the rule or the instructions. That means the model exactly that is required to produce that answer. For example, say you have a lot of information, or you have the past 10-year data for your atmospheric data, say of particular place from Pune, IUCAA, nearby IUCAA. You have all the 10-year data, and you know that in each day how the temperature varies, and depending on that, you know whether that day it is going to rain or not rain. Okay, so you have the data and you want the answer. You have the answer like it will rain or it will not rain. Okay. So from the past 10-year data, for each day, temperature or cloud concentration, etc., you have an answer for that. So you use your machine learning algorithm to predict what is going to be today, whether it is going to rain or not. Based on today's data, you don't have that answer on that day, but you have all the data for the past 10 years and the answer along with it. Okay, so this is the basic difference between the classical programming or and machine learning program. Okay, usually the machine learning algorithms are used to classify or used for two different kinds of problems, and they are applied for two different kinds of problems. One is for a classification and another is for the regression. Okay, one of the most successful machine learning algorithm is called the artificial neural network. There are many uh, machine learning algorithms are there, and the most successfully applied algorithm is one of it is ANN or artificial neural network. Neural network actually process information in a similar way the human brain does. Okay, the network is actually composed of a large number of highly interconnected processing elements. They are called the neurons. They are working in a parallel to solve a problem. Uh, that means you are familiar with the biological neuron. This shown here. Similar to that, we have artificial neurons. What exactly we do in ML kind of algorithms is we are actually mimicking the human brain. Okay. For that, there are biological neurons within our brain. So we are developing some neurons in our program. These neurons are fully interconnected. These neurons are connected with the uh, inner layer neurons. Okay, these neurons, these neurons means actually we are actually applying some data on it. And if you check on this, you can see that each of these input, these are called the input neurons, x1, x2, x3. These are the data. In the similar example that what I said earlier, if you have the atmospheric data, temperature, the clouds density, etc., that will be the input data. And you have these data, and these neurons are interconnected in the inner layer neurons, and that neurons, the data will be somewhat manipulated using some kind of equations. Okay, so here you can see that here it is a neural network. You have the input, you have the desired output values, and you have the this is the neural network. So it will actually do all these calculations, and then it is compared with the desired output. Whether there are errors, it will adjust the weights and then go back to the initial process. Okay, I will explain in detail in the following in the later slides. But these are called weights. W1, W2, W3 are called weights. These are just random numbers. Just to understand, you can see that these are random numbers. These are initialized when you start the program, and the weights are updated based on their how the neural networks clearly obtain the output. Okay. So it is not going to the next slide, I think. Okay. So ML, the neural network actually learned by an example. This expression, it's a simple expression that represents the neural network. You can have the input data, that is the xi, and which have some value of weights w. The weight function is actually connected to each of these data, and it has some random value initialized with when you start the program. And what you are actually doing is you are finding some correlation of your data with your answer. You have both the data and answer given. So it is actually a mapping process where the neural network actually maps the data and finds the pattern to the output or the answer that you want. Okay. The neural networks, they have a remarkable ability to drive. That means they have any complicated data or an imprecise data. They can actually extract some patterns from the data. And here in the figure, you can see that as the number of neurons increases, as the number of neuron increases, of the total number of neurons and the number of layers increases, the uh, uh, the uh, the neural network is capable of finding more complex patterns within the data. So if we use only a single layer, this is one layer, and this is the input, and this is one layer, and if you are using only a single layer, then you can maybe use it for a linear kind of regression or a linear separation of these two classes. But if you use more than one input layer, means more than one layers, that is the layers which are the in between the input layer and the output layer are called hidden layers. Here only one hidden layer is used. Here there are two hidden layers. So here more hidden two hidden layers with a more number of neurons are used. So as you increase the number of hidden layers and the number of neurons, the neural network is capable of identifying complex patterns within the data. Okay, I hope if you are clear, you understood all these up to this point. Okay, so this is the basic introduction to neural networks, and I will explain this based on some examples in the upcoming slides. You can get more details about ANN or machine learning algorithms in the following slide. You can learn it if you are familiar with Python. Then you can learn all these things. This scikit-learn, tutorial points, and W3 schools. All these are some simple sites to give a good introduction and a way for coding on these machine learning algorithms. Okay. So we are now going to the next part of our talk. Why machine learning is so important, or why we are actually using machine learning. Okay, we know that the current technology, right? The computer vision and the machine learning actually transformed the entire digital world. You can simply say that you are living in an era of data explosion. There are a lot of, if you are going, some examples are shown here. For every 60 seconds, the total number of tweets or status updates or messages or all these comments or data created, it goes on increasing. It's moving from gigabyte to zettabytes. So what happens is that when you have a lot of data accumulated, you need to analyze this data properly for the retrieval of information from it, right? But the problem is, if you have a large amount of data, that means if you have a lot of works pending, you are not able to do any of it because you are overloaded, right? Similarly, if you have a lot of data accumulated, it is not possible to analyze in a usual way. And another important thing is, sometimes you cannot actually perfectly define what exactly happens with the data, but with some example, without any some examples. So you cannot actually identify the relationship or the correlations hidden inside these large amount of data using conventional method. There are a lot of other okay. There are a lot of other kind of problems involving how humans cannot analyze these huge amount of data, right? Then what will we use is, we will go for some automated techniques. Like, that's why the ML play an important role now. The machine learning tools actually model human wisdom. The machine learning algorithms is capable of discovering the relationship between the variables of a system when you have the data and the outcome from it. So that is the main advantage of using machine learning algorithms. And machine learning algorithms are clearly defined using statistical models, and they have mathematical models. Their statistics, they use the theory of statistics for building their mathematical models, and they are applied for a large variety of applications currently. Okay, so that is the main cause for using machine learning in our normal life. But now we are discussing about why machine learning is important in astronomy. We know that observational astronomy has accumulated a large amount of data with the recent advancements in our detector technology. These large scale surveys and large scale surveys and observatories actually span the full range of the electromagnetic spectrum from radio to gamma, and the total amount of information occurring each day is goes on increasing. Okay, and it's like the data sets, the order of magnitude actually we are accumulating every day is actually goes on increasing. So the problem is we are on the horizon. That means astronomy has come into a big data era. And here is some it's a workload chart showing the data accumulated by the various surveys and observatories per night. So can you imagine 90 terabyte of data, analyzing this much amount of data per day using human power or human in a conventional way? No, it won't be possible. Okay, so we are in the data explosion era or the big data era, and it's like the small data we can actually do it by ourselves, but for large amount of data we cannot do it by in a conventional way. Okay, so that is the reason why we are introducing as machine learning techniques in astronomy. Okay, there are, if you search in the archives, you can see from 2015 onwards, it's like deep learning papers you can see in astronomy. And so before that, before 2000, you can see neural network, but they are few. But after 7 or 8, you can see multiple uh, uh, machine learning algorithms used for astronomical data research, because the main reason is that astronomy has a lot of data, and most of it is archived data, and people are generating results or are doing analysis on this archival data, not once, but they are doing it many times, multiple times. Okay, and they use the latest technology or the latest algorithms to analyze all these. Okay, so if you search in internet, you can see that in astronomy, many problems like photometric classification of a star, galaxy, quasar, morphology classification, photometric redshift, transient detection, noise detection, then uh, merging galaxy identification, many problems, gravitational lensing. So, and even the with the simulated data for the cosmological data, all people are applying machine learning algorithms for getting a better result. Okay, so we will next discuss about how machine learning algorithms works. Okay, so in this, I will just briefly explain a simple problem, and then I will show how it is exactly working. So we are here considering a star galaxy classification problem. That means if you have some data, say you have a star data and a galaxy data, and you want to write a program or a machine learning algorithm. Once we train on the algorithm, it will tell you which is a star and which is a galaxy. Okay, so the first step is to take a sample of known objects. Okay, before entering into this part, I would like to say in machine learning, we are usually using three or machine learning methods can be classified into three. One is supervised, second is unsupervised, third is the semi-supervised, and there is a other kind of reinforcement learning is also there. In supervised learning, it is like a teacher teaches in a class and the students learns from the teacher. It's like that. That means the teacher shows an apple and tells you this is an apple. Okay. So you know that what is an apple and how it is different from another fruit. A similar way in computer, you have data and you have the class and you have the labeled data. That means for apple or for star, you have all these data. For galaxy, you have all these data. Like that, you have a labeled data in case of a supervised classifier. In case of unsupervised classifier, it is like a you have to cluster. That means similar kind of objects are clustered together. The unsupervised techniques also require training, but you don't need a labeled data in that case. Okay. So this algorithm, in this example, I'm actually describing a supervised classifier where you have the data and the label. That label tells you the data belongs to a star class or a galaxy class. Okay. In order to take a sample of objects, what do you have? You have a sample of non-objects is required. That means you need to know a star, whether the data corresponds to the star or it is corresponding to the galaxy. Next, second one is extract some distinctive features from it. That means extract some features of the star and the galaxy. What it means exactly? You know, from the image, you can see that it is a point source, but galaxy, star is a point source, but galaxy is a resolved object in the nearby universe. If you are going to classify star and galaxy in the nearby universe, then you can see that the star is a point source, but galaxy is a resolved object. You can see the features, like if it is a spiral, you can see the spiral arms, like that. Okay. Similarly, you can extract some of the features based on these images. Like if you check the PSF value, the point spread function of the star, you can find the FWHM from the galaxy profile. You can find the major axis diameter, like it is the star is a point source, so it is different from that of galaxy, and the flux with a certain aperture. So similarly, so you can consider all the relevant features which can clearly separate the star from galaxy. So extract some meaningful features from the data. So the third point is what? Train the machine. Once you have extracted the features, you have the data features. That is your data. The extracted features is your data. And you have extracted the data from star or galaxy. So you know that whether the data is extracted or the feature is extracted from a star or a galaxy. So you put the label of that data inside that. Why the label is required? Because we are going for a supervised classification. Okay. So in the third step, we are going to train our algorithm. Okay. In the training process, what is exactly the algorithm do? The training means you hope you remember that equation, or we just figured the nodes are connected to the neurons, right? And during training, the random values of these weights are updated every time. And what it exactly doing is you have these features. Say you have 10 features extracted from your images, and these 10 features are your input. These are your input values, input data. Then you have some weight parameters. The weight parameter is updated every time. This weight parameter is multiplied with the data, plus some acquisition function is there, and each of these each of these data multiplied by the weight parameter got summed with some bias, and some acquisition function is also there. And after that, whether the algorithm is capable of finding some pattern of all these stars using all this data, whether using all these values, whether it is able to map the input data with the class. If it is not able to map it, then the weight parameter is again updated. So it is like the random value. First we are using some random values, and based on the calculations, if there are error means the actual value and the predicted value. If there is some error, then the weight parameter is updated again, because only the value which we can manipulate is the weight parameter. What not we are manipulating, only the code can manipulate is the weight parameter. Okay, so this process is continuing. Then what happens? This is what I like wrote here. First, it trains the data. Then it need to test. What means by test? Test the network with the new data. That means after the feature extraction, we actually divide the entire sample, the training sample, into two parts. One is used for training, and another set is used for testing. For training, we use the entire training data, and we'll keep some of these known values with us. That is called the test data. The test data is used for testing the network, whether in that case we are providing only the data without any layer. Okay. Then the model just predicts that value, and then it compares the predicted value with the model with the actual data, and see whether it is capable of classifying the entire data properly. Okay, so that is the test phase, and if there are errors, then you have to go back to the which phase, first phase, and then update your dates. Okay, once you have tested the data with proper accuracy, say for example you have 90% accuracy, or 95% accuracy, or 99% accuracy, or 100% accuracy, you can go for classification of unknown data. That is your advantage. That means if you have 1000 stars, 1000 galaxies, you have extracted all the features, you have trained the machine, and you have tested the machine, your algorithm with a 95% accuracy, then what you can do, you can go to a survey, download some objects, extract these features, then give it to your machine. Then the machine will predict whether it is a star or a galaxy based on the based on their model. Okay, so how it is, how it will help you. So this will help you because you have accumulated a lot of data, and you cannot analyze it conventionally. And if you have developed such models or intelligent machines, you can analyze these data within few days or weeks. So it is simple, right? So finally, we are expecting a classification just like this, but don't expect always like this. It won't be possible because it's astronomy, and we have a lot of anomalies associated with different data. But in an ideal case, we can say like this. Okay, so this is how machine learning algorithms works. So in a simplified way, you have to get the data, clean and prepare your training set, train your model, test your model, and if there is some error or you need to improve it, then update the model. And once you have this updated model, you can use it for unknown data classification. You have this machine learning algorithm, you have this prediction, you can go for manual validation by humans. Why? It won't be possible that all these data predicted by our machine learning algorithm will be the same. There will we said only 95% accuracy. That means out of 100, there will be possibility for 95% accuracy, right? And if there are some anomalies that you have found in the data, you can actually update your training data. With that, you can update your algorithm. Okay, so once you have developed such a model, you can use that model for training any kind of data. That means once you have trained for classification of stars and galaxies, the algorithm or the model can be used for it. But the same algorithm can be trained with some other kind of jobs, like classification of some cat and dog images. So that is the advantage. Okay, so now I will discuss briefly some of my research work. I won't go much deeper into the details of the algorithms used, but I will describe what are the applications that we can use with these machine learning algorithms. Okay, so the first problem is the quasar detection. So you are almost completed 1 month in the summer school, so you know all about what is meant by quasar, aging, etc. I just wrote it here. Distant galaxies which have a bright center at the bright core, which appears to be a point source in the images, and these resembles like a star. So distinguish these point-like objects from star is very difficult if you take images. Okay, and these distant galaxies which have a bright core are called active galactic nuclei, and such an AGN, a subclass of such AGN is called a quasar. They are very bright, very luminous objects in the universe, and you need to identify or identify these quasars because they are very important to understand the evolution. Okay. So if you take two images, if you take an image of a star and a quasar, these are the images from SPSS. You can see that you cannot actually distinguish them with these images, right? But if you take a star and a galaxy in the nearby universe, you can distinguish with your visual inspection itself, right? But it is difficult. This is, you can say that this is somewhat larger, small. No, it depends on the images that you take. May change. Okay, so how can we distinguish the star or the quasars from these stars? Okay, we know that the stars are the quasars. We clearly get the class of the object from their spectra, right? Spectra are like the fingerprint. So the one solution is like you will get you go and get the spectra on the objects, and then from the spectra you can distinguish the stars and quasars. You can see it from here. You can see that the star spectra mostly consists of the absorption lines, and the quasar spectra which have broad emission lines in it. So clearly, very easy, right? But the problem is that spectroscopy is not that easy. It's very costly, based on time and money, right? You will get an image with 54 seconds of exposure in SDSS, but you may take hours of exposure for getting a spectrum. Okay, and you can imagine that there are more than billions of stars in our galaxy. So to obtain the spectra of all and analyzing these, it's not an easy job, right? And another thing is, for spectroscopy, you will need bright objects. That means faint objects are possible, but the faint limit, there exists a faint limit, right? So all these are problems, right? What we can do next? So the solution is, we can actually go for objects, and we can look or observe these objects through the different windows of electromagnetic spectrum. Okay, that means if you have an observatory, and if it is an optical and then like the SPSS, with the wavelength ranges from 3,000 angstrom to 10,000, then you can divide the different bands, the entire band, into small wavelength regions, and you can observe through that wavelength filter. So you will get the intensity of light emitted only in that particular wavelength using a single band. Okay. For example, in SDSS, it uses 5 different bands, and the bands will observe the objects only in that particular wavelength region. That means they are filters, right? Okay. So you will have a magnitude, or you will have a magnitude for each of these stars in all these filters, and the ratio of the amount of these magnitude is actually the flux. It's the intensity is right. The flux received in 2 different bands is called the color in astronomical context, and you know all these things. And the most important thing is this color. That means you know that the magnitudes are expressed in logarithmic scale, so you can directly subtract it. That's why, say, if you have U, G, R, 3 different bands, then U minus G gives you one color, G minus R gives you another color. And if you plot some of the objects in this color feature space, you can see that these objects lie in specific colors. In this example, you can see that redshift less than 2.2 quasars are lying in this area. Some of the hot stars are lying in this area. Redshift greater than 3 quasars are lying in this area. The cold stars are staying here. Okay, so that means you can use the astronomical color as a feature for distinguishing star from quasar. And this is what we did in our first problem of identifying or classifying the unresolved objects. So we classified the objects as star, galaxies, and quasars. And this is a similar plot as shown above. We have, you can see that this is what we got after we train our model, and then the result. You can see that some of these non-quasars are lying here. These are redshift less than 2.2, and some of the high redshifts are lying here, the red color. The green color is the stars. The orange color is the late type of stars. And the hazy points, you can see some of the galaxies because we choose a particular color window, and that's why most of the galaxies are eliminated by using that color itself. Okay, so we use a classifier, a machine learning algorithm, which is called a difference boosting neural network. Okay, I'm not going much deeper into that algorithm. For identifying or for classifying stars, galaxies, and pulsars. So we use SPSS data. SPSS have 5 different filters. So we will get 4 primary colors, but we will use all the colors. That means 10 colors we use. And our machine learning algorithm is capable of identifying certain patterns within the data such that they are exactly classified. So with that trained model, the accuracy what we got during the test phase is like 99% for pulsar data. And we are still, it's in the last month, I just compared the our catalog with the SDSS non pulsars. We will get 90% accuracy. Still, it is showing 90% accuracy. For constructing the catalog, we are also getting 90 to 90% accuracy at that time. Okay, so the advantage is this. Once you have constructed this machine learning algorithm, we are capable of classifying or constructing a catalog of 6 million unresolved photometric detections in SPSS. And we predicted out of the 6 million, okay, 3.5 millions are stars and 2.4 million pulsars in that color space, and a small number of galaxies. Okay, so can you imagine by using even this color, you are just sitting in front of a machine and try to automate some of your code to classify these 6 million objects without a machine learning algorithm. That is a tiring work that you cannot. So this entire classification, if once you have trained your model, training process is somewhat time costly, and you need processing power also. But once you have that trained model, you can use it for classifying 6 million objects within 30 minutes. Okay, so that's how ML makes your life more easy. Okay, our second kind of application is transient detection in LIGO data. Transient detection in LIGO data means we are finding some of the glitches present in the data. Okay, don't worry about all the terms inside this. This belongs to some of the names of the noises present in the data. And what we exactly do here is transient means you have some flux variations for a small time, right? They call it as glitches. These glitch distribution over there are LIGO is a very complex system, and there are multiple subsystems inside that, and there are different noises associated with even the subsystems controls. Okay, so the different noise signals like seismic earthquakes related or some control signals, auxiliary optics, a lot of glitches may be there. What they cause is like it's like they give some false alarms. That means LIGO is for detecting gravitational waves. These false alarms producing means due to this presence of these transients or glitches, it may mimic like the GW data. Okay, so we need to detect this, and we need to remove them. That is the main purpose. So here we did this work in 2015, 16, and at that time we are not able to get any real data. But at the end of that work, we'll able to get the real data. So first we started with some simulated data and some of the hardware injections that they are purposefully done within the system to see whether the systems are running properly. Okay, and later we will have the oven data in the first release of the data. Okay, so to classify these glitches, we use, in case of simulated data, we used a supervised classifier. For hardware injections also, we used a supervised classifier. And for real data, we use a hybrid classifier. That means we use an unsupervised classifier plus a supervised classifier. It is like, I could say that we use the same supervised classifier used for the classification of unresolved objects in case of this. That means we use VPN here. Okay. So I'm not going deep. That means hybrid classifier means first we use some unsupervised method to remove some of the basic glitches, and then we use the supervised classifier for the labeled data. Okay, so this is the confusion matrix. Confusion matrix actually shows the accuracy of your prediction with a true class on one side and a predicted class on another side. So these are the glitches we used for classification of used for the classification of the glitches. That this much glitches we used. Okay, so you can see that the accuracy. So this kind limb, it is 100% accuracy we got. For different kind, there are accuracy varying is there. You can see a low accuracy at this particular value, and the wrongly corrected or the wrongly predicted is like true false negatives. Like your model is actually predicting a wrong class, but it belongs to the same class. Why these wrong classifications are going? Because your features exactly matches with, if the features of two classes matches, or the boundaries of the two classes coincide, then you will get these wrong predictions. It is not because of any problem with the machine learning code, but it is due to the presence of features that makes or confuse our network such that they are sharing the similar values. That means SN has similar value that of CSP. That's why it is predicting in a wrong class, predicted to a wrong class. You'll get more information about this in this paper. Okay. So I said, once you have developed a model, then you can use it for any purpose depending on your data. You only need to train your model. Okay. So now, as I said earlier, we are using machine learning algorithm. Means it's in the earlier case, for the last three problems, we are using the machine learning algorithm, but we are actually extracting the features from the data. We are not using the data directly. We are extracting some features from the data. So that is called the classical machine learning techniques, or the traditional. But in some cases, we are not able to extract some features, or in some cases we don't want to extract some features. We want to give that image as it is to the machine learning algorithm and ask them, try and do your classification by automatically extracting the features required for that. Okay, can we say that like that? See, you can see some of the applications, right? You know, this is a facial recognition problem. You know these things, right? Because when you upload a photo in Facebook, automatically ask you to tag your friend from that group, right? How it is recognizing? If you try to upload a video in YouTube, if you some of the content is not properly referenced or without any reference, then they will ask you, right? They will give you suggestions that is not uh, properly referred, so you cannot do that. In even Google searches, if you just what if you have a page and if you want to search in Google, when you started typing the first letter, Google will give you the suggestions, and in most of the times there will be one that you exactly prepare. Okay, if you go to Amazon, what happens? If you search for a shoe, then by the next day onwards, you will get recommendations from Amazon that a new brand shoe is coming, or you can view that, etc. So all these things use machine learning algorithms, but not in a traditional way, but in an advanced way. Okay, what is the advantage? Or what are the advantages? You can directly use the entire data. You can directly give the images. So our problem is, can we apply such kind of methods in a field of astronomy research? For example, uploading a photo. So it will automatically tag you. It's a bird. It's in this figure. It's a dog and a baby. Okay. So can we tag exactly like that? If you upload an image of an astronomy image, it is tagging like, oh, it is a galaxy. It's a star. This is a quasar. Can we do that? Or if you have a number of images, can you cluster them? Like all the birds together, animals together, like all the galaxy images with the same morphology together. Is it possible? Yes. This is possible with another technique called deep learning. This is the new paradigm of machine learning. It's actually not new, it's unknown. It means machine learning. We described artificial intelligence in the first and the second slide, right? So artificial intelligence is achieved using machine learning algorithms, and deep learning actually is a subclass of AI. Okay, so it is not the first phase. It's already started in 2015 itself. Deep learning applied to astronomy. The first problem is the Galaxy Suit Challenge by Delma. Okay, and this was a you may be familiar with the terms Kaggle. There are a lot of Kaggle challenges going over, and in 2015, this was the challenge that they have a Galaxy Zoo of images, and you were asked to build a machine learning model which can classify the galaxy morphology using the classifications given by the user or the uh, Galaxy Zoo challenge team, and build that model. Yeah, it was actually built in 2015, and with a great accuracy. That was it's almost near the human accuracy. That is the advantage. Okay. So what exactly changes when we are moving from a traditional machine learning to a deep learning? So in a traditional machine learning, we have an input data. We need a domain expert, or you need to know what exactly need to extract from these data for the correct classification. Okay, then a classifier then the output. But in case of deep learning, you have this input data, you have a deep neural network. It is called a convolutional neural network. We are using that. It will automatically identify the features from the data or extract the features and then will give you the output. Okay, I'm giving you a very, very basic idea and you can develop it based on this. So our next problem is application of this deep learning techniques to astronomy. That's what we did. And it is applied for the identifying the morphology of the galaxy. There are many morphological parameters or morphological features. One of these feature is the bar present at the center of the galaxy. Okay, so our aim is to identify or detect the bar galaxies from a group of galaxies where we have both the data, bar data and unbar data. Bar data means galaxies which have bars in it. Okay, so this machine learning and deep learning techniques, we are using a convolutional neural network, and this is also a supervised kind of network. That means you need both the data and the label for training your network. Okay, hope I clear. You are clear with all these. Okay, why we are choosing this bars? If you are asking why we are choosing this bar, there are many other important morphological features. Yeah, you can easily identify whether the galaxy is elliptical or spiral or lenticular, whether it has closely tight spiral arms or not. All these can be selected, but bars are very important because they gives you information about the evolution of the galaxy, and that's why the reason why we are selecting all these selecting the bar galaxy for this study. There are many ways to detect bars in galaxies. The most important one is the visual identification. That means you need to visually look uh, visually examine all these galaxy images, and that person says that okay, this has a bar, this has a small bar, a nuclear bar, or that kind of classification can be done. But that is not an easy job, and you cannot go for much amount of data. Okay, so for training our convolutional neural network, we have used 3 different catalogers. Why? Because these persons classify visually the galaxies. Okay, so what we actually do is Nair and Abraham had a visual classification of galaxy morphology. There are more than 14,000 galaxies are there, and they have classified with the means all these features inside it. If it is a spiral, elliptical, whether it has a bar or ring or etc., all these features are mentioned. Okay, so what we did is like we just downloaded a data set from SPSS, and then we cross-matched our data that are the galaxy data with the Nair and Abraham. Similarly for Hawley and for the Galaxy Zoo data release 2. All these have information about whether they have a bar or not. Okay, and then we cross-matched all these catalogs with our data, and we found that there are some 3,800 barred galaxies, 5,400 unbarred, and thus a total of 9,400 nearly that much. total galaxies. So we have the bar galaxy image with the label from one of these candidates. Okay, these two tables shows just cross-matched included, means that it cross-matched with our data, and we just included only 776, and we have just neglected the rest because they have some other kind of some saturation effects or blurred images. So only perfect images we took from the data. Okay. Once we have these data, that means in convolutional neural network, we are using the images of these galaxies. Okay, we can process or pre-process some of the images. They have some 256 into 256 pixels in size, and the central region is always bright, so you can actually normalize that with the subtracted with the mean value image of the galaxy. That means if you have 3000 bar galaxies and generate a mean file, and then you subtract that for every image. Okay, so don't worry about this. This is what the network model. Okay, this network model uh, consists of 5 different convolutional layers and 3 fully connected layers. Don't worry about that. Because of the time limit, I cannot actually go much deeper into that model. Just go and check what is meant by a convolutional model, and because it is different from the usual machine learning algorithm, it is extracting the features. It is convolving actually the features from the image. Okay, so this is what we get. This is the result, our final result. This confusion matrix shows that there are means our we have this total 9300 something images. Out of that, we divide the entire data into training and testing purpose, and our test result is actually shown here using this confusion matrix. Okay, this confusion matrix tells that 1100 bar galaxies were identified correctly with bar, and 2568 galaxies identified correctly with the without bars. Okay, there will be a small incorrect predictions are also there. These incorrect predictions may be due to different reasons. Maybe it is not actually a bar, but the central region looks like maybe there will be an arm or the nuclear bar. So there are many other reasons for that. So the total accuracy of our classifier is like 94.1%, and that was very good at that time. It's in 2017. So in deep learning technique. So I will just stop with this, but I want to say that the same model you can actually train for identifying a different feature, right? So that is the advantage of using machine learning algorithms. So how will you understand whether your machine learning algorithm correctly picks or correctly identifies the features? These are called the feature maps. This filter visualization of these our network, the different convolution neural network layers. The output of the convolutional neural network are shown here. If you take an input image of a bar galaxy, you can see that the bar structure you can see. That means it determines or it identifies that particular feature within that image. But if you go for an unbarred case, you cannot see that kind of. So with these kind of understandings, the network is capable of identifying that particular pattern at the center. Okay. So this is third one. I actually can't cannot explain the NLP part. This is another work. So I didn't do. Maybe I'll do it in another time. Uh, so I would like to say that current techniques or the all the available facilities in our it's due to this COVID situations, most of us know how to access data, this information or training. There are many multiple courses available, so you can go for one of it, like data analytics or data mining or machine learning. Then you will understand exactly uh, how beautiful it is, how can you design all these, and how the machine learning techniques makes our lives more easier. Okay, so once you build a model, you need to train your model for another set of data, but the training part is still there. You need to identify everything, but still you can say that you have a model and you can do that anything, classification or regression or reinforcement learning, everything with that. Okay. Thank you.
Thank you very much, Sheelu. Are there any questions in the chat? Or if any participant wants to ask questions, you may also raise your hand. Although we have gone beyond the time, we can maybe take a few questions.
There are few questions in the chat box.
Okay. Also, there's one hand up. If you, okay, yeah, please go ahead with the questions in the chat.
Okay. So one is first one is, ma'am, could you provide some links, I think, where we can learn these machine learning for free along with some ebook? Yeah, you can directly. I have shown some of it in the slide itself. I can share that slide. I have already mailed that to Sandosh, so maybe he can upload that slide in the common site. And scikit-learn, W3 schools or tutorial points, all these are where you can learn machine learning. But if you search, you will get thousands of pages explaining the code for a single data, means like an example data you will get. Okay, so all these you can use it for your study. So the second question, ma'am, is it possible to attain 100% accuracy? Okay, 100% accuracy. If the features are that great, then you will get 100% accuracy. But as we are all these problems I have described here is astronomy related, so there will be some anomaly, some missing values, some kind of saturated data. So all these provides some noise in the data that causes the reduction in accuracy. Okay. Next question. Hope that will be okay. Also, since we know exactly where the machine goes wrong, we will have to check the data manually. Isn't that against the motive behind ML? It's not like that. We have to visually analyze some of the test images. I can say that we have constructed 6 million objects as a catalog, and we classified using our trained model with 2.3 million cursors. But if you ask me if all these predicted cursors are cursors itself, that I cannot actually completely say that it is true, because we don't have that 100% accuracy in our prediction. But what we can do is, with all the available data, I can say that in the test phase, we will get 99% accuracy or 90% accuracy. And only in the testing phase, you can actually go and check manually and see if there are some anomaly present in the data. and remove it and then retrain it. Otherwise, you need a system like a Galaxy classification system, a citizen science project, where machines are classifying and people are also classifying the galaxy morphology. And this vote fraction is taken as an input so that the machine automatically retrains its model according to the vote fraction. That means it is like you are doing the training in after a certain time or for a certain period like that. Okay. So the other kind of thing is like that means you cannot actually go it for a prediction phase, but you can go for a test phase where you can identify the exact reason why this anomaly or why this low accuracy happens. There is another thing also. That means if you get 100% accuracy in the test phase, but when you go for a prediction, you will get all wrong answers. That is called the inability to generalize to a problem. A machine learning algorithm need to generalize, like it overlearned. If you have a small amount of data, the model may be overlearned so that by giving your test values, it automatically says, oh, this is this, this is this. It is like it's 100% confidence it's giving like that. But that won't be applicable to a prediction data set where it is not generalizing the model to a unknown or unseen way. Okay. So hope I answered all in the chat box. Any other queries? Or
I don't see any hands up.
okay. So
yeah, sure. So if you want to share any materials, then you can send it to Santosh and we can upload it to the
I have I have already shared it with Sanush, so maybe he can upload that material and do the
sure.
Okay. So thank you. Thank you for
very
giving
much.
such an thank you very much.
All right. Okay.
Bye. Bye.